So in the last lecture we studied inertia subgroup and its a specific subgroup of inertia subgroup called wild inertia. And as I told you in the last lecture and the lecture before that, we want to study Galois group of finite extensions of number fields, and our strategy is going to study decomposition subgroups for a lot of primes of the number field. And to study the decomposition subgroup, we saw that we can do it using inertia subgroup and quotient, and then wild inertia and its quotient, etc. So we are going to pursue this course a little bit further and study decomposition subgroups by realizing these decomposition subgroups as Galois groups of local fields. So these are completions of number fields at various primes or infinite places. So we want to study all these things. So today's lecture is going to introduce the concept of valuation and local fields, and this is what we will do in this lecture and perhaps next couple of lectures. So theory of valuations and completions. Okay, so to begin with, we can take any field K. So definition, let K be any field, an absolute value on K or it is also called multiplicative valuation on K is a function which we will denote with these double lines from K to real numbers, but only bigger than or equal to 0. So, only positive real numbers. So, these are all R in R such that R is greater than or equal to 0, okay, such that what are the properties? 1, valuation of 0 is 0. Valuation of alpha is bigger than 0 if alpha is not equal to 0. Okay. So, any non-zero number will have valuation different from 0. 0 is the only element of K which has valuation 0, and then valuation is multiplicative. So, valuation of alpha times beta is valuation of alpha times valuation of beta. This is the reason it is called multiplicative valuation. And then last is kind of an important property, there exists A bigger than 0 such that valuation to the power A satisfies triangle inequality. Okay. So, this is what the valuation means, all right. So, this A is independent of alpha and beta, that is why I wrote at the end that valuation for all alpha and beta in K. Okay. So, we do not often there is you would see definition where A is always taken to be 1, but we are not going to do this. There is a related notion of valuation where instead of you kind of work with log of this, so multiplicative becomes additive, etc. But this is the definition that we are going to work with. Okay, and in this one, 0 inside the valuation is different from 0 that is sort of on the right hand side. 0 inside the valuation is 0 in the field K, and 0 on the right hand side is the real number 0. Okay. So, two valuations, let this and sub 2 be two valuations on K. We say that valuation 1 is equivalent to valuation 2 if there exists a constant C bigger than 0 such that valuation with respect to 1 is Cth power for all alpha in K. Okay. So, this is when we say that two valuations are equivalent, because you see if you have a valuation and you raise it to any power, any positive power, you still get a valuation, right, and that is a very cheap way of getting another valuation, and maybe it does not give you anything new, you might guess that, and indeed it does not, and that is why we define the notion of when two valuations are equivalent. Okay. So, here is a lemma. So, it is clear that if two valuations are equivalent, then they induce same topology on the field K. So, let me actually take a step back and say right. Okay. So, if this is a valuation on K, then d of x y, if you define it to be x minus y to the a, is a metric on K, right. What you learn in the first analysis course or maybe a basic point set topology course. So, this gives you a metric on K, and hence you get topology. Once you have a metric, you can get topology on K, right. I mean, having a metric is stronger than getting a topology. Okay. So, you turn K into a metric space, right. Now, the distance of course depends on the choice of valuation, but the topology on K, so does not depend on the choice of the valuation as long as two valuations are equivalent. Okay, let me say that again. Equivalent valuations on K induce same topology on K even if the metrics are different. Okay. Two different way of defining distance on a space can give you the same topology, right. Okay. So, the converse is also true, and that is the lemma that I had started stating. If one and two induce the same topology on K, then they are equivalent. Then and 2 are equivalent. Okay, so the converse is also true. Equivalent valuations induce the same topology, and if you have the same topology, then the two valuations are equivalent. Okay, and so that's very nice. Okay. So, so what are we given? We are given that valuation 1 and valuation 2 induce the same topology, right. So, if I have is any valuation on K, then saying that valuation is less than 1 is same as saying that valuation of x to the n goes to 0 as n goes to infinity. This is same as saying that x to the n goes to 0 as n goes to infinity. Okay. And this last statement depends only on the topology. Okay. Therefore, valuation of x less than or equal the first valuation 1 of x less than 1 is equivalent to saying that valuation of the second valuation of x is less than 1. Okay. All right. So, that is what we have established, right. So, we have already established one link between the valuation. We still have to go a long way to show that they are equivalent, but at least if valuation with respect to the first one is less than 1, then with respect to the second one is also less than 1. All right. Now, if valuation of x, now what I want to do is I want to choose, let me put it this way. So, choose x 0 in K such that its valuation is less than 1, but x 0 is not 0. Okay. All right. So, if I want to do that, well, why should such a thing exist if valuation of x 0 is bigger than 1, then valuation of well, okay, let me, I did not do basic properties of valuation for you. So, let me do them here. What is valuation of 1? Right. So, valuation of 1 is valuation of 1 times 1, which is equal to valuation of 1 times valuation of 1, which is valuation of 1 squared. And so, if x is equal to x square, then there are only two options for what x could be. It could be 1 or it could be 0, but 0 is the only element of K with valuation 0. So, this means that valuation of 1 is 1, right. So, if valuation of x 0 is bigger than 1, then valuation of x 0 inverse is less than 1, right. So, if there does not exist x 0 in K such that valuation of x 0 is less than 1, then valuation of x is equal to 1 for all x in K minus 0, right, which means that it is the trivial valuation, right. So, this means that So, if such a x 0 does not exist, yeah, maybe I will put 1 here everywhere. Hence, valuation of x with respect to 2 is also 1 for all x in K minus 0, right. And hence, valuation 1 and valuation 2 are equivalent. So, this is the trivial case, right. If valuation is 1 for every non-zero element of K, then they are trivially equivalent. Okay. If that is not the case, then we can always choose such an x0. So, that is a bit pointed, but anyway this is what it is, right. So, what I do is you take C such that valuation of x0 with respect to 2 is valuation of x0 with respect to 1 to the power C, right. So, what is C? C is log of x0 over log of x0 1, and this is the reason why we do not want valuation of x0 to be 1, because then we will have log will be 0 and this will not make any sense, right. Okay. Now, so what I can do next is, so this is now I mean this is my C, this is the C we want, right, but we still have to prove the same relation for any x in k minus 0, not just x0 but for all x this should happen. So, what I do is I take x in k such that valuation, the first valuation of x is less than 1. Again, if valuation of x is bigger than 1, then I will just replace x by x inverse, okay, it is not going to make much of a difference. So, take lambda bigger than 0 such that valuation of the first valuation of x is first valuation of x0 to the power lambda. Again I just take lambda to be log of valuation 1 of x divided by log of valuation 1 of x0, right, and that makes sense. So, what are we going to do now? I want to show right, I want to show that, so what do we want? Let us remind ourselves what we want. We want to show that valuation of x, the second valuation of x is first valuation of x to the C, right, for this particular C. Okay. So, to do that, what I am going to do first is I am going to show that the lambda that I have here with respect to first valuation also satisfies the same equation with respect to the second valuation. Okay. So, what I am going to do is I am going to, so my lambda a priori is just a real number, I have no idea whether it is rational, integer or anything, and I can't know. So, what I am going to do is it is easier to work with rational numbers. So, I am going to approximate this by rational numbers. So, let m by n be a rational number such that m by n is bigger than lambda. Okay. So, what do I get then? I get that yeah, how do I yeah, okay, let me do it this way. So, this means that valuation 1, which is x0 to the lambda, is less than x0 to the m by n, right. Okay. Yeah, I think I have gotten it the other way around. Yeah, sorry, valuation of x0 is less than 1. So, if I raise it to a larger power, I get a smaller number, right, like half to the power 4th is less than half to the power 2, this kind of thing. Okay. All right. So, what do I have then? I have that valuation of x to the n by x0 to the m is bigger than 1, which means that valuation of x0 to the m by x, sorry, these are all first valuations, is less than 1, right. So, now once I have that, what I get is valuation of x 0 to the m by x to the n, but with respect to the second valuation is also less than 1, right. Okay, so I can rewrite this as valuation of x0, sorry, not x0, valuation, the second valuation of x is bigger than second valuation of x0 to the m by n, and this holds for any rational number m by n which is bigger than lambda. Now similarly, I can show, you can take this as an exercise, if m by n is less than lambda, then second valuation of x with respect to 2, if second valuation of x is less than second valuation of x0 to the m by n. Now taking limit as m by n approaches lambda both from left and right, we get second valuation of x is second valuation of x0 to the power lambda, okay. All right, and what does that tell you? So that tells you that second valuation of x is second valuation of x0 to the lambda, which is equal to first valuation of x to the c lambda, which is equal to the first valuation of x to the power c, and that is what we wanted, right. Hence, and 2 are equivalent. Okay. So amazing, we have proved the converse, that if two valuations give the same topology, then they are equivalent. Okay. All right. So now we will restrict ourselves to number fields, right. Whatever we did up to now holds for any field, but now we want to go back to our number fields and study valuations on them. Before I do that, let me make a side remark. This is a digression, not part of this course, but the theory of valuation has become important in recent times, even more important in sort of last 10-15 years with the work of Peter Scholze, who defined what are called perfectoid spaces, and it's a great way of doing p-adic geometry. And so he not only considers valuations with values in real numbers, but you have valuations with multidimensional valuations, etc. And that has become really important in number theory now. Okay, Peter Scholze got Fields Medal in 2018 for his amazing work. And whatever we are studying forms a very basic step of his theory. So it's even more important that you understand this very well if you want to do algebraic number theory in a very modern way, especially with sort of p-adic Langlands program, etc. Okay, so so let's get back to number fields. So now let K be a number field So what's nice about number field is Z is contained in K, right? Z is contained in Q, which is contained in K. Let this be a valuation. So whenever I say valuation, I mean multiplicative valuation on K. So we say that this valuation is Archimedean if there exists M in Z such that valuation of m is bigger than 1. Okay. So, it will turn out that Archimedean valuations, valuation of every m other than 1 and 0 will be bigger than 1. Right. So, it means that if you keep adding 1 to itself, you can get numbers with arbitrarily large valuations. Okay. So, you can get large numbers in some sense. So, this is why it is called Archimedean, because he is the first person to articulate the fact that if you take any epsilon bigger than 0 and you keep adding it to itself, you can get very large numbers, right. So, he wrote a book on it, on large numbers. And we say that this valuation is non-Archimedean. So, this is not the sort of system that we usually encounter until we start doing number theory, algebraic number theory, if valuation of m is less than or equal to 1 for all integers m. Okay. So, you keep adding 1 to itself, but you never get anything with valuation bigger than 1. Valuation always remains bounded inside a bounded disk. So, there are these two very different kinds of valuations that you can define. You know, even this definition you could make for any field which contains a z. Okay. So, any field of characteristic 0, but we are going to restrict ourselves to number fields because that is all we are interested in, and we can get a clean answer. So, the next question one can ask, what are all valuations on a number field? Okay. So, what we are going to do now is we are going to first look at examples of valuation, and then in the next class next lecture I am going to tell you that these are all the examples there are. So, let us look at some examples. So, look at Q, right. Now, you can embed Q inside R, and then if you define it like this, where this is the usual modulus in R, this is a valuation on Q. Right. There is a reason, I mean, of course, you do not need to go to rational numbers to define modulus, but there is a reason I am doing this. This will be clear in some examples, maybe third or fourth example that I am going to give. Now, let P be a prime number okay, and you can write, so K is again Q. Now, you can write x in Q minus 0, take any non-zero number x, you can write it as P to the power R A by B, where R is an integer, A and B are integers, and P does not divide AB. Okay. So, you can always do this, and then you define valuation, what is called p-adic valuation of x to be P to the minus R. Okay. And so, here is an exercise. Is a valuation on Q, right. So, this is called p-adic valuation. So, these are two examples of valuations, and in the next lecture, we are going to prove that these are all the examples of valuation up to equivalence, right. Of course, these are not all the valuations, because you can raise it to some power and you will get another valuation inducing the same topology, but up to equivalence these are all the valuations on Q, and in fact we will prove a similar result for number fields. So, I will start the next lecture by giving examples of valuations on general number fields, and then we will show that those are all the valuations up to equivalence. Thank you.